So I'd like to now, so we've discussed a little bit about the fundamental issues associated with global energy. And John Strickland has just given us a very useful update of his analysis of some years ago concerning the comparative issues with ground and space solar. I gotta hasten to add that this is not to say, and if anybody is following the ground solar market, this is not to say that there is not an enormous opportunity for terrestrial solar power as witnessed in the explosive growth in that market. There's been just tremendous growth in ground solar. But all of that ground solar comes in the context of baseload power provided from other sources. And so John's comparison is really apples to apples if we wanted to use space solar to offset ground solar then, as opposed to not. So John certainly didn't argue that there's not a tremendous market for ground solar. The marketplace shows it's just going crazy. It's very likely that for the foreseeable future, the next several years, that demand will outstrip supply for terrestrial solar power.
Just in context, however, for terrestrial solar power, we continue growing at 31% annually, globally. 20 years from now, we will achieve 1% of electrical load.
That's because it starts from such a small percentage of such a very large number. Absolutely. But that's one reason why there's such a tremendous opportunity there at the moment. Now we're going to turn to the question of the solar power satellite.
And Seth Potter, who's formerly worked with Marty Hoffert in New York, and several years ago joined the Boeing Company, will discuss this with us.
Thanks, John, and thanks, Daryl and the other John, because I think the talks segue nicely into this. Basically, what I'm going to talk about are some studies that we did at Boeing under contract to NASA, and the team included several people who are going to be speaking today from Boeing and NASA, including Mark Henley and Joe Howell are both here. And we had a variety of other experts at both locations who contributed to some of the technology studies. Basically, I'm going to get into 5 different technology areas that were studied over the course of 2 different contracts. And the basic idea is, as John Strickland alluded to, and as Daryl was leading up to, the solution to many of our environmental and economic problems may lie in solar energy from space. And the traditional solar power satellite, which collected energy in space and beamed it to the Earth, was rather large and heavy. And as John Mankins has pointed out in a number of meetings, the cost to first power was so huge that people started to wonder if one would ever get built, because it seemed that you couldn't build a small one. So how do you get started? So in order to do that, we developed some smaller scale applications for collecting solar energy in one location and in space and beaming it to another. The first one on the upper left corner of the screen we call the power plug, and what that is that's a power beaming satellite. It is based on the International Space Station array, but has a laser or microwave power beamer. And what that does is it beams power to satellites either while they're in the eclipse period or to augment solar power at the end of the satellite's life. It's kind of a utility in space. The next concept, the Mars Clipper, doesn't beam power, but we did do a study of a large solar array. That is, what would you do if you can collect tens or hundreds of kilowatts in space? And one of those things is you can power electric transport to Mars. Now, those first 2 concepts are relevant to solar power satellites in another way, and that many of the schemes for solar power satellites involve modular construction in which the pieces are launched to low Earth orbit and self-transport to a higher geostationary orbit through electric propulsion. So what both of these concepts have is solar-powered electric propulsion. So they're kind of the early incipient stages of an eventual large solar power satellite. Now the third concept that we studied, alternative solar power satellite architectures, is a reinvestigation into the traditional large-scale geostationary solar power satellite, and we look into a variety of different ways one might do that. And this was all done around the late 90s or early 2000s in the NASA Space Solar Power Engineering Research and Technology Program, which seeks to reinvestigate solar power satellites. When we had completed that, we got a follow-on contract to study cryogenic propellant depot in space. The rationale for that being that for large amounts of what this device does is it receives tanks of water launched from the Earth, electrolyzes it into hydrogen and oxygen, and liquefies the hydrogen and oxygen and stores it until it's needed by vehicles going to the Moon, Mars, and so on. The way that relates to space solar power is since such a propellant depot would need something like half a megawatt of solar energy, what we wanted to do is look into applications of solar energy in space that are much larger than the current satellites, the largest of which are 10 to 20 kilowatts, but much smaller than the hundreds of megawatts to gigawatts of a solar power satellite. Basically what it is transition to a solar power satellite. Now, the fifth concept that we looked at, which was done under a separate concept also to NASA, a separate contract, I should say, was a beam-powered lunar rover. And this is an idea that comes up in some of these conferences, where what you do is, if you want to explore some of the shadowed craters on the Moon, which never see sunlight, we looked into the idea of using a rover that receives beam power, because in the lunar poles, there may be regions that never see sunlight that are near or not too far away from regions that always see sunlight. So it may make sense to collect the power in one location and beam it to the other. I'm going to quickly go through some of the specifics. It's kind of a contradiction in terms, isn't it? If you have specifics, you kind of want to dwell on them. Oh well. A little more on the power plug. It's basically it's based on the International Space Station array and produces a little over 60 kilowatts. I think that this was a slight optimistic version of the ISS array, although John, you tell me that actually I was being rather realistic. So that basically what you have here is an ISS, an International Space Station solar array powering, it's hard to see, but you can see a parabolic reflector, and our baseline concept involves a laser, because lasers, you can beam large distances. We have an alternate concept that uses microwaves.
Right here, you have a pointer.
Okay. Okay, thanks, John. Yeah, right here you can see the parabolic reflector, which focuses the laser beam. And as you can see, lasers don't diverge much with distance, so you can beam thousands of kilometers from places that are not in the Earth's shadow to places that are. An alternate version uses microwaves, and there you need to, you're using a lot of the power to match orbits with the customer, get nice and up close and personal, and couple with the satellite via a microwave link. The disadvantage there being, or the advantage there being microwave conversion is very efficient. The disadvantage there being most satellites don't have microwave receivers designed to receive lots of power. They do have solar panels. So our kind of baseline idea is to use a laser, but you could have a microwave version. Basically, you can use it for any reason you want several tens of kilowatts of solar power. Wireless power transmission, or very high bandwidth communications of a space probe, or we looked at, and you'll see some applications where space-based laser radar or LiDAR, that sort of thing. Another incremental concept towards space solar power, this is another step upward in power, up to around 4 megawatts. The solar power satellite sun tower concept was a concept devised by John Mankins, where you have kind of a long string of solar collectors supplying, I think, roughly about a gigawatt or two of power to the Earth. What we did was we kind of squared off the arrays, cut them in half, and basically took 2 of them and used it to power a spacecraft whose main purpose is a a radar mapping spacecraft, and the idea is you can send this off to the moon or Mars, and you have a very high power radar beam which may be able to penetrate the surface. I chose the 5.8 gigahertz frequency because that's a frequency that's proposed for power beaming. So in a way, although this is a radar mapping spacecraft, but it's also kind of a test bed for space solar power technology. Again, you see we go from 60 kilowatts to 4 megawatts, thereby showing the idea that there are incremental steps you can do between a 10 kilowatt communication satellite and a 1 gigawatt solar power satellite. So we're step by step, we can get there. I think the current term is spiral development. When John Mankins was coordinating some of these studies, he devised the term mission system concept. So we had I think the power plug was an MSC1. This was MSC3, and if you're still awake at the end of my talk, I'll explain what MSC2 is. Mission system concept being various steps to a full-scale solar power satellite. The Mars Clipper was an electric vehicle, and that was, again, demonstrating collecting large amounts of solar power and using it to power electric thrusters, kind of demonstrating the idea that you can have modules of a solar power satellite that self-ferry. And so this explores Mars and demonstrates space solar power technology at the same time. The other thing is we want to, in order to make the transition toward full solar power satellites, we of course want that mass to get higher and higher so we can demonstrate handling large amounts of mass in space. And this thing weighs about 60 metric tons, far from the thousands we'll need, but getting there. Let's skip this one. One of the things we did was we studied how to beam the power, and the traditional solar power satellite used microwaves because microwave conversion is very well understood and very efficient. Back in the 1970s, when solar power satellites were first studied, laser power transmission was looked into and kind of, pardon the expression, dropped off the radar for a while for a number of reasons. Lasers in those days were very inefficient, so your solar power satellite had to be extra massive. Yes, Darryl? Yes, they have, and I'm going to show you where we were in 1999, and some of you, if any of you know even some more recent information, you can maybe make suggestions on how I can tweak my numbers. We did, in fact, reinvestigate the laser, and the motivation was when we re-looked at lasers, and I'm zapping myself, aren't I? Really taking a close look. When we re-looked at lasers, it seems that the main reason to look at them in the first place is, as I mentioned before, and as this pointer demonstrates, they don't spread out a whole lot. If this were a cell phone, the energy would be all over the room. Now, you want it to be because you want people to pick it up. But once the beam spot is small, then you don't have to collect a lot of power to fill the spot with energy on the ground. Therefore, the whole system scales down. So it kind of makes, that's kind of the reason you want to look at lasers in the first place. The other reason is microwaves do have the potential to interfere with communications. If the wave is not nice and sinusoidal, you'll get harmonics, which means you can interfere with higher frequency communications. The other thing is, as I'll show later, some of the energy spills beyond the receiving array, and so that can interfere with communications. This beam of light, if you turn on your cell phones, which I hope you won't during my talk, but if you do, you notice I can shoot this laser all over. It doesn't interfere with your cell phone. Now, it's got some disadvantages. It is blocked by clouds, more so than microwaves. But the beams are so tight that multiple sighting of the receiver may partly mitigate that. Nevertheless, I don't claim it's a panacea, and there the microwaves have the advantage. Another advantage of optical wavelengths or lasers is that dual use of the infrastructure. That is, a rectenna, that is a receiving rectifying antenna used for microwaves, all it can do is receive microwaves and convert them to electricity. But the receiver for a laser beam solar power satellite is simply a photovoltaic array, and even if the solar power satellite weren't there, it can still receive sunlight, although the design might be somewhat different as far as what wavelength you optimize it to and so on, but nevertheless, you still get some use. Now, the dual use of the land, there's advantages and disadvantages to both. I guess Darrell or John, one of you guys pointed out that you can have crops growing under this. So the receiving arrays for the microwaves have been compared. If you design them right, some people claim it would be like chicken wire over telephone poles, that enough light would get through to grow crops under it. The optical wavelengths, you can put them, you can't grow crops under it if it's catching all the light, but you can put them on top of building rooftops. And I was thinking, in fact, in terms of you have a building like the Boeing 747 final assembly plant, which is so large you can fit Disneyland in it. And so you've got a large, I don't remember, but oh, okay. Thanks for the detail. But the basic idea is you have a large consumer of power and you have a large surface to collect it. Whereas you may not want microwaves impinging on an industrial facility. The rest of it I won't go through, but you can kind of imagine what some of the safety and perception issues are. Well, I want to direct your attention to that last item. PMAT is power management and distribution. The 1970s reference solar power satellites were enormously heavy. They weighed 50,000 tons for a 5 gigawatt reference satellite, and we believe that that was optimistic because they tended to underestimate the mass of the power management and distribution. You would need enormous amounts of cabling and lots of shielding to prevent the corona and arcing discharges in the plasma of space. We tended to underestimate that. With lasers, that can be, at least to some extent, mitigated because you don't have to have a central beaming station on the satellite. That is, you can have many panels on the satellite, each with its own laser. And I'll show you what they look like. For the alternative architecture solar power satellites, we looked at 4 options. 2 different ways of generating the power, that is photovoltaics or solar dynamic, which is basically heat engines, and 2 different ways of beaming the power, which is either microwaves or lasers. So if you have 2 different ways of generating the power and each has 2 different ways of beaming it, that's 4 different options. Now, that first one, photovoltaic power generation, microwave power transmission, is your classic solar power satellite. By the way, Darrell, this kind of addresses your question. This is a little bit out of order here, but this axis shows the transmitter efficiency. This shows the receiver efficiency. These contour lines show overall efficiency. So when I did this chart back in the late 90s with input from my colleague Mark Henley, who will talk to you later, microwaves were about up here, lasers were kind of down here. I believe there's been an overall trend moving to the upper right side of this chart.
When you say microwave, I was asking about lasers, millimeter wave.
Millimeter wave, that's a good question. I think they're kind of around here, but I'm not sure. That is, I don't think they're nearly as efficient as microwaves, but I would guess, like everything, they're getting better. When we looked at this a couple of years ago, we felt they were more expensive and less efficient. But it probably deserves to be looked into again. This is our alternate concept for a microwave beaming photovoltaic array in space, beaming power to the Earth. What this is a modified version of an idea that John Mankins had originally thought up, where you have many circular arrays. We decided to make them rectangular. This is almost like a gigantic Venetian blind, and at the bottom of it, this is 16 kilometers long by 500 meters wide and delivers a total of 1.2 gigawatts into the grid. It weighs about 23,000 metric tons. The mass per unit power is worse than the 1970s designs, even though these are lighter materials, but that's because the 1970s study was a little bit optimistic. Basically, again, it's sort of like Venetian blinds with a big transmitter at the bottom, and these Venetian blinds rotate to track the sun. Here's a photovoltaic laser concept. This is the microwave concept, and you see at the bottom here this large microwave transmitter. This backbone here, which delivers the power from these arrays all the way down to this microwave device, is extremely massive. So if you go, and this thing is no walk in the park either, so what we tried to do is lighten it up by going to laser. And you can see here's the laser version, and each solar panel has its own beaming apparatus, eliminating that massive backbone. Unfortunately, with the assumptions we made about laser efficiency, which were not that great a few years ago, the whole thing expands to 55 kilometers because lasers, we believe, were less efficient overall. Again, we haven't looked at this in a few years. The numbers may have changed. Laser SPS and terrestrial photovoltaics. Again, the idea here is you may be able to first build photovoltaic terrestrial power plants and then later on augment them with satellite power. It's an advantage of lasers over microwaves. The ground asset has use even before the space asset is built. We looked into the idea of whether you need to rotate the Venetian blinds or not. If you rotate them, you can track the sun, but basically the farther apart, the closer together you pack them, the more likely they are to get in each other's shadow. And there is kind of a shadowing effect in the middle at midnight and at noon, and they get in each other's way. Now, what happens is you get because of the shadowing, you get an energy profile like this, where basically at midnight there's no power. At 6 a.m. and 6 p.m. you're at peak power. At noon there's no power because the thing is edge on to the sun. Now, Mark had the idea that since the daily electricity demand also has two peaks, if you collect solar energy on the ground, it's got a profile like this in the middle of the day. If you collect it in space by one of our sun tower arrays, it looks like this. If you combine them, it looks like this, which mimics the daily electricity demand pattern. So the advantage of lasers is that the laser power from the satellite plus the natural sunlight may be able to roughly mimic the daily electricity demand pattern and minimize the need for storage. A little bit more about one of the system drivers to any kind of power beaming is any kind of power beaming, microwaves, lasers, or whatever, has kind of this energy profile. If you exaggerate the vertical scale, you can see these things called side lobes, which are kind of energy that forms off to the side of the main beam. Imagine this is a beam incident on the ground. You put your receiving array here, but you've got energy spilling over, which can interfere with communications. In terms of laser light, these are not significant, because basically this will be too dim to see. If you can't see, it's not hurting anything, not much anyway. With microwaves, this beam is intense enough so that this might interfere with your cell phone or whatever. It's something you may need to fence off an area around the receiver. Possible advantage to lasers, you might be able to overlap the beams. I think I'll skip a lot of this. This is the solar dynamic concept. Basically, you've got a couple of hundred little heat engines all feeding to a centralized antenna. And this is about 2.5 by 3 kilometers on the side. Compare that to 5 by 10 in the original 70s reference design. Similar idea, but laser power beaming. We're short on time, and we're going to hear more about fuel depots later, so I think I'll skip this quickly. Suffice it to say, this was actually a 700 kilowatt array, which received tanks of water, converted it to hydrogen and oxygen, and stored them in liquid form. Last thing we did was we developed a beam-powered lunar rover prototype. This actually received, we actually had a demonstration rover which received beam power on this receiving array here, about a meter square. About 100 meters away was a microwave transmitter. And yes, we really did drive this under beam power. Furthermore, in one public demonstration, This rover was in the Santa Ana Mountains, about 30 miles from here, and the drivers were attendees at an open house at the NASA Marshall Space Flight Center in Huntsville, Alabama. So, okay, first step was Huntsville to LA, but eventually we'll be able to drive them on the moon. And I'll skip the key points and conclusions because I think I spoke fast enough so nobody's forgotten anything. John, do we have any time for questions? Okay, I'll take one question. Sir.
On the power plug concept, where would the satellites, the arrays be located? Are they at the GEO so that they can reach the lower satellites as they...
We looked into both. You can have a geosatellite, and one idea is to put it outside of the eclipse region and beam into it, and another is to have them in LEO and perhaps store energy and get up close to the customer satellite and beam power to it. I think we're out of time, so thank you for coming.
One of the dilemmas for the laser power beaming case that we identified early in the Fresh Look study in the mid-90s is that with a somewhat larger beam expander, it's quite easy to get at temperatures on the ground that are above that of the ignition of most complex carbon-based structures like trees and houses and cities. And so if you think there's an issue today with nuclear proliferation, you have the problem with Iraq and them enriching uranium, imagine that 30, 40, 50 years from now, you had a hypothetical country, somewhere in the world that wanted to launch several gigawatts of laser power station with large apertures because they said that was what they needed. And then how would you wrestle with that in the international community? Now, there are ways to deal with that with the right regimes, i.e. very small beam expanders a long way away. But a beam expander in GEO, which is no problem on the ground, the same exact system deployed in LEO gives you very much a James Bond kind of system in space. And so lasers, although they're very attractive from the standpoint of the spread of the beam, they have their own, and interference with RF systems, they have their own issues in terms of their deployment and their operation in a geopolitical environment which is less than idyllic. So there are issues, and there are pluses and minuses on both sides. Ultimately, all of these things are going to have, if any system like this goes forward, or even any terrestrial applications of wireless power transmission, they're going to have to get resolved through the International Telecommunications Union, which manages spectrum and its applications, and it's going to require... that was good. That was good. I did okay. I did well. It's going to require the introduction of any major new energy technology is going to require a lot of development on both the technical side and the geopolitical side. I think we're almost ready. We shifted the order just a little bit. So in our order of march, what we've had our discussion of why, the discussion of ground versus space, the quick discussion that Seth was able to offer us of some of the concepts that had been looked at in U.S. studies. I will just mention that there was also a fairly significant study a couple of years ago conducted by the European Space Agency looking at ground versus space solar power with a somewhat different perspective than that John Strickland articulated. It was a European perspective, and it really looked, because Europe is at such northern latitudes, at the potential for putting a large either ground solar or space solar arrays in the southern parts of Europe, in their sun belt or in North Africa. If you want to look online for those, there was a nice paper on that subject on the European studies presented a couple of years ago at the International Astronautical Federation.